Okay, so for the majority of the rest of the year, we're going to be doing function study. Basically, it's function study and probability. And you can do probability functions, but we're not really doing probability functions as such. But what we do is we unpack more and more complex functions as we go along through the year. Okay, so the first unit we very deliberately choose to be algebra, because effectively the skills that you learn in algebra are the how. Like when you learn how to factorize, it's so that you can get it into null factor form, into factor form, so you can use the null factor law to work out what x is. And the reason why you want to work out x is because they are the x-intercepts of a function. So almost all of the stuff that we've done in the algebra unit is now going to be revisited and utilized within the function units throughout the rest of the year. Okay, so the reason why I've got this graphic up is because these are just the shapes of functions, lots of different functions that have been illustrated as dance moves. I think it's very important. If you're a mathematician, that's basically how you dance. And you can see there are some regular functions here. I'll just use my cursor so that's captured on the video, like a straight line graph here. Then you've got a parabola, x squared, x cubed, sine x, cos x, tan x, cot x, which we don't do, 1 on x, which we don't do. So lots of different functions here. So there's a whole bunch of different functions, all from the simple, like y equals x, to the more complex. You have to say that's a fairly complex dance move, right? Y equals 1 on x, which we don't do, but nevertheless, there's a whole bunch of complex functions here. So the function unit is applying the algebra processes that we did for the last 6 weeks or so, and see how they sort of fit in with functions. Now, the reason why we study functions at such depth is that really at the heart of it, at the practical heart of it, I suppose, is that's what scientists do. That's where the mathematics comes in for scientists. What scientists do is that they gather data, and then based upon the data that they've gathered, they then create mathematical models which represent that data. Mathematical models are functions. So if you've got a function which represents a set of data, you can then use the function to do predictions of that data, like extrapolate out into the future or interpolate within the function to work out values that you don't have actual data points for. So it really is function study. Knowing functions and how they work is really at the heart of any further study you do in science, as well as sociology, psychology, economics, etc. Understanding how modelling works is really important. Now, in mathematics, we're more interested. Although we do modelling, it's kind of almost like a tack on at the end of the unit. Like now that you know functions, try doing these application problems. But in actual fact, so for a mathematician, what we want to do is we want to get an idea about how functions work. Yeah, does that make sense so far? Okay, cool. So classic examples of scientists gathering data and creating functions from, think of things like climate change, think of things like pandemics, or the pandemic, I should say, and how they modeled, where we need to, how we need to reduce the numbers in 2020. We're looking at these logarithmic graphs and all these kinds of things in order to predict how this virus was going to grow so that we can then produce a response to it, remodel it. Oh, if we do this, what will the new modeling be? Oh, I can see it's now tapering off a lot more sharply. That's mathematicians doing it. Well, scientists working with mathematical models doing that, trying to work out what the variables are, popping them in, seeing how it changes the predictions for the future. So that's basically it. Oh, and if you're a conspiracy theory, then scientists are making up all the data and using the modeling just to for their own evil ends, if you're a conspiracy nut. So what we're doing in the first unit is polynomial functions. So if you remember from the algebra unit, we looked at what makes a polynomial a polynomial. Do you remember what it was? What makes a polynomial a polynomial, Em? Doesn't have to be 3 or above, but the powers have to be. It is about the powers, though. Someone said whole. Who said that? No, it's just Egbert, my imaginary friend sitting there. Egbert said whole numbers. So yes, well done, Egbert. Well done. So they have to be whole numbers, otherwise known as integers. Is that you, Joe? Man, with mask on, this is interesting. And they also have to be positive. Good. Okay, so polynomial functions have whole, non-negative whole numbers. So, for example, and I'm writing this on the board just for the video, I'm saying it. Technically, this would be a polynomial function. It's y equals 7, because you could write that as y equals 7x to the power of 0, right? Pointlessly, but nevertheless, you could do that, because anything to the power of 0 is just itself. So that's a polynomial function. So that 0 is not positive, but it's not negative either. So non-negative. Y equals 7x is also a polynomial function, because the power of x is, say it loud, say it proud. Thanks, Lockie. 1. Okay, so remember that's an implied power. If there's no power there, the power is implied to be 1. So that's y equals 7x to the power of 1, as is y equals 7x to the power of 14, etc. plus x cubed minus 1. So that's another example of a polynomial function. Now, our polynomial functions don't go above 3 in this unit. So we look at powers of 1, or powers of 0, but they're a bit dud. Powers of 1, powers of 2, and powers of 3 polynomial functions. Okay, so non-polynomial functions will be like y equals 1 on x squared, because that could be written as y equals x to the power of negative 2. So that's why 1 on x squared is not a polynomial function. Okay with that? Okay, so polynomial functions. So what we're going to be doing is we're going to be starting with linear functions, which is a bit basic, I know, but there's a reason behind it, and that is because a lot of the procedures and processes that we do are basically identical from unit to unit, or from section to section. So we need to be across things like gradients. We need to be across things like x-intercepts, y-intercepts. We need to be across things like turning points, or stationary points is the more general term, asymptotes, and a bunch of other things as well. So what we do is we build our knowledge up. So we start off with linear graphs, which have the least critical information in them, basically gradient, x-intercept, y-intercept, just one of each. And that's it. And then we move to quadratics, which have those things as well as turning points. And then we go to cubics, which is the power of 3s, which have those things plus inflections and or stationary points and stuff like that. So we build it up. Then we go to log graphs and exponential graphs and cyclical graphs. And they've got special features that apply to those functions as well. So even though linear functions is really simple, I'm going to start with describing what a function is and using keywords. So success today looks like this. You can explain what a function is, really explain what a function is. I bet if I said to everybody here, write down an example function, I bet everyone here could do it. I think you might even know the terminology f of x, I think, but you could at least go y equals something. But what does it really mean? What is the function really? Use keywords like domain and range. Okay, so I'll unpack those in a second and describe the components of a linear function. So we'll finish off by looking at linear functions today. Okay, so I'll zoom back out so you can sort of see it. These are notes that you can write in under where it says what is a function. I think it's important that you do get this down. Is that big enough for down the back? Otherwise I can zoom up. I'm not seeing any shakes of the head. Egbert, you okay? Well, get your books out. No, you can't just memorize it, Egbert. You have to write it down. When you write something down, it gets it into your brain. Yep. Okay, he's right. So a function. Often people, when they think of a function, they think of the rule. But what I've done in this definition is I've asked you to think about what we're doing. So a function takes a set of numbers as its inputs. So think of a function like a box, and you put a number into the box, and out comes a different, might be the same number, but out comes a number according to a rule. Okay, so here's our first keyword here. A function takes a set of numbers as its inputs. This set of numbers is called the domain. So if I ask you, what is the domain of this function? What I'm saying is, what numbers can this function take in? Now, for polynomial functions, they are almost always the set, get this, I'll go through this properly later, the set of all real numbers. And when I say all real numbers, that's that real thing that I had in the test. All real numbers simply means whole numbers, fractions, and radicals, which are like surds and stuff, like square root of 2. You can't write root 2 as a fraction. It's a non-terminating, non-repeating decimal. Pi is another example of a radical. So all of these things are all real numbers. Now, I can see some looks on your faces, and I'll answer the question. Yes, it is possible to have a number that is not real. And I'm not making this up. They are called imaginary numbers, and they do exist. Or they are utilized in mathematics and in complex physics like string theory and stuff like that. So they're called complex numbers or imaginary numbers. Sorry? Square root of -1 is the most basic imaginary number. It's represented by the letter I, and you do stuff with it. But I'm a mathematician, so I don't care about doing stuff with it. Okay. So what do you reckon's under that next blank here? So a function takes a set of numbers as its input, called the domain, applies a what? No, it's not range. Doesn't apply a range. Does start with R though, and it's a word that you've heard before. Starts with R, rhymes with fool. Hey, you're not silly, are you? So we apply a rule to that set of numbers, and it outputs a new set of numbers called the range. Okay, I'll let that sit with you for a second, because I need to move the slide over to the next page. But if you've got any questions, ask them now. But I do expand upon this in my next sheet. Because I'm recording this, and I'll put these notes up on Google Classroom, if I go too fast for you, leave a bit of a gap, and then know that you can fill in a bit later. Just give you 30 more seconds to write that down. But at its heart, I could describe a function simply by saying, here's a set of input values, and here is a set of output values. And I could say, that is my function. Probably not a very interesting one, but I could do that. Okay, I will move on now. Okay, so you can copy that down, and I'll just explain what I've written there. So the way it works is kind of like how I said. So as it says there, each number in the domain has a single number. So you have a number that comes from the domain, and then it outputs to a value in the range. So remember, when I say domain, I'm talking about a set of numbers. And when I say range, I'm talking about another set of numbers. Charlie, does that kind of make sense? But because it's actually, even though domain and range are new words, once you get used to them, it's a lot easier talking about domain and range than it is talking about the set of numbers I use to put into the function and the set of numbers I use to get out of the function. That's really quite tedious to say. So it's a lot easier just to talk about the set being at the domain or the range. So each domain has a single number that it maps to. That's really important, that each value in the domain can map to the same value, but it can only map to one value. Okay, so I'll just spell that out here. You can see here, what I'm trying to represent in this picture, that these dots here are like numbers in the domain, and these dots here are like numbers in the range, so numbers in the set. This number maps by the functions rule. This number maps to this dot. So does this number. That's okay. This number maps to this dot, and it's the only one, and this one maps to that dot, and it's the only one. That's okay. That's all good. What you can't have, I'm going to put it in, then I'm going to erase it because otherwise it gets too confusing. What you can't have is this. Where can I put it? I'll just do it here. What I can't have is a single dot going, I feel like I'm making a bicycle or something, a random bicycle. You can't have a single dot in the domain going to two different spots in the range. So in other words, the rule can only produce one value from its input. How does that sound to you? It is possible to create rules that aren't functions, and we'll look at them a bit later. They're called relations. So y squared equals x squared, for example, will produce a graph, but it's not a function. And I'll explain the difference later on. I'm only interested in looking at functions right now, so I'm not confusing you too much. Okay, I was meant to zoom up then, sorry, probably didn't see that. So this is where we make the link to graphs. So these mappings, it's mapping points from the domain to the range. These mappings are often presented as ordered pairs, and that's where our x, y comes from. So a coordinate on the Cartesian plane, our x and y axis, that's the Cartesian plane. A coordinate is simply a single example of a mapping from domain to range. So x is in the domain and y is in the range. dx, y, r. We call them ordered pairs because you always put the domain coordinate first and the range coordinate second. Always, always, always. Hence, it's an ordered pair. Okay. Slide 7 there. What we do when we draw a graph... Oh, yeah, Emma. Say that again, sorry. Yes. Yeah. So the inputs or the values from the domain are the x value, and the outputs or the values from the range are the y values. And it's always x, y. So I know that if I see the point 7, 12, that means 7's been input, 12 has been output. Don't know what the rule is, but 7's been input, 12 has been output. It could be that the rule is, let me see, 2x minus 2 could be the rule. Could be x plus 5. I don't know what the rule is. I'd need more points to work out the rule. Any questions before I move on? You look like you want to ask a question. So the domain is the set of values that we input into a function.
Oh, and the range is the set of values you get
output. Yep. Input, output. That's my computer scientist nerd coming out of me. Inputs and outputs to a system. Or ecology or anything really talks about inputs and outputs of systems. So a graph is a picture of it. They say that a picture is worth 1,000 words, and it's also true in mathematics. The reason why we learn how to graph is because the picture of the function often tells us a lot more as human beings who are used to looking at patterns and quickly picking up stuff about them, a lot faster than looking at a function. So me telling you that this function here in slide 8 is y equals x minus 2 times by x plus 1 all squared is a little bit meaningless. But if I show you this graph here, we can see that as x gets bigger and bigger but negative, I can see that the graph is the outputs are getting bigger but negative because it's going down ways here. I can see as well that as x gets bigger and bigger this way, in other words, as the inputs grow, they first of all go down, but then they go up and then go up forever. I can also see at this point and this point here, we have turning points where it stops being going positive and starts going negative, and then stops being negative and starts going positive. So I can pick up a lot of data just looking at a picture. Now, it doesn't tell me what the coordinates are, what's the y value when x equals 10, or what's the y value when x equals 1,000. The graph doesn't tell me that, but it gives me an overall picture of what the function is doing. It's increasing, to a point, then it's decreasing to another point, then it's increasing again. So we get a sense of what's happening. Okay, graphs should always have an X and a Y or a T and an A or whatever it happens to be, but generically an X and a Y. So what you should do, guys, is when you're drawing your graphs, your axes should always be labeled. You should always have arrows at the end of each axis. You should draw your line. And my personal preference, it is not a requirement, my personal preference is that the line that you draw to represent the function has arrows at either end. All of those arrows say to the reader that this graph goes on forever in every direction. Okay? Without them, it feels like there's a definite stop there and a definite stop there. That's just it's not just me and no one else does it in the world, but in terms of the two ways you can draw a graph with and without arrows, I prefer the arrows. Everyone would say you have to put arrows at the end of your axes like that. Okay, so label your axes, draw your line, and I recommend putting arrows at the end of your line to demonstrate to the reader you know it goes on forever in each direction. Okay, I'm going to move to the next slide. Does anyone have any questions before I move on? Okay, am I going too slow? Here's that summary for you. So, the mnemonic aid to memory that you can learn is Dixroy. Dix, domain. No, I wasn't calling anyone a rude name then. That's the first part of it. Domain, I wasn't looking at anyone particular when I said that. Domain, input X coordinate, right? DIX. Roy, range, output, Y coordinate. Okay, so that's a way of grouping what each of those different parts do. So the function takes values from a domain. It is input into the function. That is the X coordinate. The range is what is output from the function. The full set is the range. Individual values are output from the function. That is the Y coordinate. And I've tried to represent that with, you can see that I am a graphics design student. My artistry is on at full force there. We have X going into the function F and Y coming out. And that happens over and over again. X and Y variables. Sometimes we call X the what kind of variable? You should know that from science. Independent. And Y is the dependent variable. And that kind of makes sense too. That X is the thing you put in, a rule is applied to it, and then Y has no choice but to come out a certain way. Okay? Because it's based upon the rule. So Y depends on what the value of X, Y depends on the rule and what value of X was put in. Okay, slide 11, features of functions and or graphs. Using those words interchangeably there. This is what I was talking about before. Not all functions have all of these features, I should say. But the first three are common to most. Y-intercept. Not all functions have a y-intercept, but I would say well over 50% do. And all polynomial functions do. X-intercept or intercepts. Not all functions will have an x-intercept, but the majority would. All linear functions have an x-intercept. Quadratics may or may not have an x-intercept, etc. And you see in brackets there, I've got let x equal 0 for the y-intercept and let y equal 0 to be the x-intercept. And the reason why I've got that in brackets is because this is a thing that you're going to do over and over again. You're going to be told, here is a function, graph it. And you need to get into this rhythm. And it's best if you work in a pretty process-driven way. You're going to go y-intercept, let x equal 0. Substitute 0 in for x, solve for y. X-intercepts, let y equal 0, solve for x. You'll just do it. Number 3 is gradient. Now, gradient is a complex beast. Simple with straight lines, not so simple when we get further along the field. But gradient is another key feature of a graph. Understanding the gradient of any graph is really important. And other critical features I've got down there, down the bottom there. Do you want me to zoom up just for a tick so you can see that? Because it's a bit small, isn't it? Is that a bit better? So that says stationary points. Stationary points. Don't write stationary points. So AR is in a car that's parked on a street, stationary, still. Stationary, like paper. Stationary is paper and stuff. So stationary point. A turning point is as an example of a stationary point. It's because it's a point on the graph where the graph kind of is still for a moment before moving on. So think about if I threw a ball up into the air, it would create a parabola, and it goes up and is still for a moment before it falls back down to earth again. So it's a stationary point. Asymptotes. That's how you pronounce it. Practice it so that when we get to them in middle of term 2, you won't be calling them asymptotes or asymptotes. Asymptotes. And importantly, very importantly, etc. Good, okay. So that is it in terms of overview of functions. Now, we're going to be a little bit behind in this unit because I don't normally start with an overview of functions, but I decided to this time because then we can start using the language straight up, and it means it's going to be less of a bit of a shock to the system when we look at it a bit more formally later on. So this is a fairly informal look, believe it or not, but it's all the groundwork for it. And then we need to look at things like set notation and stuff like that to describe the domain and describe the range and stuff like that. But I want you to be able to use those words. Okay, so linear functions. There are 3 forms for a linear function. So I'm now just, the rest of the lesson is just now focusing on the first, I suppose, fundamental learning for the polynomial functions unit, which is linear functions. And because you've been doing linear functions since year 8, I'm just putting a bit of formal info about it so that you can move on with it. And there may be some things you haven't seen before. Can I zoom up on slide 12 or are people still on slide 11? Just waggle a paw in the air if you're still on slide 11. Nah, cool. So there are 3 forms. It's important that you see all 3 forms. It's basically how a form means how it is written down. So there's the gradient intercept form. So the gradient intercept form has the gradient in it explicitly, and it has the y-intercept in it. And this is the one that you are most familiar with. It looks like this. Yeah? You're all familiar with that, right? Because M is the... Yep, and C is the... Right, that's all. The point-intercept form, I'm not sure whether you would have seen or not. It looks like this. I'm not going to explain what it means, though, so just take it in verbally or write it down for yourself if you need to. Y minus y1 equals m outside of x minus x1. Okay, I will explain verbally, but that's the form of it. If you're asked to write something in point-intercept form, that's what it looks like. Now, point-intercept form, basically the x1 and the y1 is like a known point. Let's say it's 2, 3. Then it will be y minus 2 equals m outside of x minus 3. Okay? So it's an actual known point. That's why we've got x1 and y1 there. They represent a known point. And then the m is just the gradient. So this is a legitimate way of writing a linear function. I don't like it, but it is legitimate to write it that way. I only like this way. I'll explain why in a second. The general form looks like this. I've got it there for historical purposes. I don't think you need to actually know the general form. I'm worried that tasks sometimes throw stuff in like the real field and you go, what is it kind of thing. So I'm just putting it there for FYIs, really. AX plus BY plus C. So for example, 3X plus 2Y plus 7 equals 0. Now the important thing to note, I think obviously, is that any one of those forms can be manipulated until it's into any one of the other forms. Yeah? It just can be. If that doesn't make sense to you, we'll talk about it. But basically, if I gave you gradient intercept form, you could work out a point, and because you've worked out a point, you could then write it in point intercept form. Or if you had it in point intercept form, you could, expand this and add y1 to the other side, and you get it into y equals mx plus c form. So you can just change the formats there. Okay, I'll zoom out and go to the next one. This is stuff you know, right? So I'm not going to waste too much time on it. The y-intercept, just reminding you, that means let x equal 0. And y equals mx plus c is the format we're using. So we're using the gradient intercept form. And we've already spoke about this, so I'm just going to write it down. 0, c. Now, what I really want you to get into the habit of doing is when I say what is the y-intercept, please don't say 3, say 0, 3. It just gets you, it's not, look, if you said y equals 3, I'd be okay with that. I know what you're talking about, right? But what saying 0, 3 does is it makes me understand that you know that what it means is that when x equals 0, y equals 3, 0, 3. Ordered pair, 0, 3. It means that you understand that the y-intercept is when x equals 0 on your graph, and then you go up the y-axis to 3. So saying 0, 3 reinforces to yourself over and over and over again, it's not just a number, it's actually a coordinate. The y-intercept is a coordinate. Gradient. That's not blowing anyone's mind, is it? Rise over run. I think we've done that since grade 9 at least. So gradient is rise over run. So as m gets, don't worry about that middle bit for a second, as m gets bigger, what happens to the gradient? Does it get steeper or flatter? Steeper, yep. But I want to just give you a bit of fancy terminology around it as well. Because as the m gets bigger, I've got bigger in inverted commas because when we say bigger, we normally mean like positive, don't we? But if it gets bigger but negative, it's also big, right? Like, e.g. money. Like if you owned $1 billion, that'd be a lot of money, right? If you owed $1 billion, in other words, negative $1 billion, that's also a lot of money to be in debt. So in other words, whether it's positive or negative, $1 billion is big. So when I say when m is bigger, I mean positively or negatively. Yeah. Further away you get from 0 is a good way of putting it. So what I'm going to say is m goes towards positive or negative infinity. Positive or negative infinity, the gradient gets steeper. What happens when m is negative though? Yeah. So that's, I think I've got, is this right? That's positive from your perspective, isn't it? For the video, I'm just putting my arm in the air. And then if it's negative, but the same value, it'd be flipped over that way, wouldn't it? Okay, so negative makes it downward sloping left to right, and positive makes it upward sloping left to right. Okay, and I'll keep that zoomed out now. As m gets smaller, what do you reckon that I'm going to put there? M approaches what? Yep. As m approaches 0, the gradient gets flatter. When m is 0, it's flat as. So it's a horizontal, it's parallel to the x-axis would be the way of saying that. Does that make sense? So y equals 7 is an example of a graph where the gradient is 0. And so y equals 7 would just be a flat line. It would be something like this. I'll erase this. That would be y equals 7. Doesn't matter. I input any number I input, every number in the domain maps to 7 in the range. So it's just 7, 7, 7, 7, 7, 7 all the way along. Graphs, by the way, I didn't say this earlier. Graphs are effectively a gigantic dot to dot, where the dots are so close to each other that you can't see any separation between the two. Okay, does anyone know the formula for gradient? Yeah. Again, I'm just briefly going through this to make sure our notes are complete, really. y2 minus y1 over x2 minus x1. where, don't write this down unless you need to. Okay, easy as. Y2 minus, now it doesn't matter which way you, where the coordinates are, as long as you get them round the right way each time. So as long as you match up x1 and y1 and x2 and y2. And the formula makes sense. Y2 minus y1 will give you the difference in y values. So that'll be your rise. And x2 minus x1 is really the change in x values, which gives you your run. So it's rise over run. Y2 minus y1. Sometimes, and you can write this down if you want to as well. You probably won't want to. But sometimes I write it down as delta y over delta x. And delta means change in. So it's change in y over change in x. That'll be useful for when we do calculus, but not so much now. So delta equals change in. Okay, moving on to the next one. So now I'm just going to do a few examples, and then you'll get some work to do for the rest of this lesson, which is not very long. So I want to do it really quickly because I know that I've spent a lot of time talking, and I apologise for that, but not to be helped. Okay, so this first one, find the gradient of the line passing through 2, 3, and minus 2, minus 3. So basically, we just identify one set as x1, y1, and one set as x2, y2, and then we go for it, really. So this would be minus 3, minus 3. So that's y2 minus y1. And then I've got minus 2, minus 2. And that would be minus 6 over minus 4. And that would be 3 over 2. Is that okay? Now, just as a proof of purchase, I'll just do it again really quickly. I'm writing a bit too big for this. I might just zoom up so you can sort of see it. M equals, it doesn't matter if I get the points around the other way, it'll still work. So if I go 2 minus, sorry, try that again. 3 minus 3 over 2 minus 2. So I basically swapped the x1, y1 coordinates over. I'm going to get 3 plus 3, because minus is a plus, 6. 2 minus 2 is positive 4, and I'll get 3 over 2. So you can see that it doesn't matter which one I call x1, y1, and which one I call x2, y2, as long as I'm consistent. So there's one pair, there's the other, there's one pair, there's the other, because the negatives will cancel out. So you'll end up with the right gradient regardless. Okay, example 2. Find the gradient if y-intercept is 0, 3 and passes through 1, 6. So there's a couple of ways you could do this. One is to use mx plus c, right? So I don't know what m is, but I do know the y-intercept is 0, 3. So it must be mx plus 3. I know it passes through 1, 6, so I can go 6 is equal to m times 1 plus 3. M times 1 is 1, and then subtract 3 from both sides, m equals 3. Yeah? Or, and I haven't left myself a lot of room here to do this, or you could just use the gradient formula. So basically, part of your toolkit selection is to go which way is going to be faster. You could go 6 minus 3 over 1 minus 0, which is equal to 3. So either way. Okay, one more example then. I'll leave it there. What if you've got the graph? Okay, so I'll leave it zoomed out. So if you've got the graph, it's basically a matter of picking out the coordinates from the graph. It might be drawn on graph paper, in which case you might, this is just a sketch, right? But it might actually be on graph paper, which means you might have to count the boxes to work out coordinates. But basically, you just need to find 2 coordinates. So in this case, what's the coordinate of this one? And what's the coordinate of that one? Yeah, great. So M is equal to 4 minus 0 over 0 minus 6. Again, don't be lulled into thinking you should put the biggest number first. You keep the coordinates. So I've got 4, 0, so 0, 4, and I've got 6, 0. 0, 4, and 6, 0, always. And that is equal to 4 over 6, which is equal to 2/3. So the gradient is 2/3. Sorry? Yep, thank you. I should have seen that it was negative because of the way the graph was facing, right? So 0 minus 6 is negative 6. And just a note, 4 divided by negative 6 overall gives you a negative number, right? It's positive divided by a negative. So as a note, if you've got 4 over negative 6, you should then say it's negative and then a positive fraction. So negative 2/3, not 2 over negative 3 or negative 2 over 3. It should just be negative fraction. That's it. So we are running a little bit behind schedule. I wanted to go a little bit further than this. That's okay though, because I front-ended with some stuff about functions I don't normally do. So for this lesson and complete for homework, please, which shouldn't be too much of a trauma, because you've got all the way till Friday to do it, is to complete exercise 2B as per learning schedule. The learning schedule is on Google Classroom. It was posted about 9:30. I've only got the first week done properly, and I just wanted to make a quick point about the learning schedule. What I've done this time, I've done sort of minimal adjustments from last year when I did it. Last year when I did it, I think what I did is I only put shortcuts in. So when you look at exercise 2B, you'll see that it says questions 1, GH, IJK, etc. Read that as they're the minimum you have to do. If you feel like you're not getting it, maybe go back and do A, B, and C or something like that to sort of backfill it a bit, to make sure that you're sort of really consolidating. But as long as you do those minimums, then you'll be good to go. And that's all I'm expecting to see in your weekly scan. Okay, so exercise 2, I'll leave that up on the screen. Get stuck into it.